Dear colleagues and members of the committee, my name is Christopher Yaroslav Libyshin, representing Lviv Polytechnic National University. Today, I'm honored to present our paper titled Design of a Unified Microservice Architecture for AI-based Financial System using Explainable AI and Retrieval Augmented Generation, co-authored with Dr. Anna Schilling. Let us begin with the relevance of the topic. The financial sector is rapidly transitioning into a data-centric ecosystem. Artificial intelligence and machine learning are no longer just experimental or auxiliary tools. They are fundamentally restructuring modern banking architectures. Today's users expect highly personalized, real-time insights into their financial health, which drives the massive demand for the integrating advanced AI directly into personal financial management application. However, this rapid adoption comes with critical challenges. If we looked at contemporary studies, most focus on isolated algorithms. For instance, training a model just for credit scoring or fraud detection. But they fail to explain how to safely integrate these models into a unified enterprise system. Furthermore, the financial sector is highly regulated. We cannot deploy black box AI models that cannot explain their decisions. Additionally, the use of large language models presents the severe risk of hallucinations, where an AI might give completely fabricated financial advice. These systematic gaps must be addressed. Therefore, the aim of our study is to address these gaps by designing a comprehensive and scalable microservice architecture for a personal financial management system, which we named FinAI. Our goal is to create a unified blueprint that seamlessly integrates large language models, retrieval augmented generation, explainable AI, and open banking standards into a single, highly secure environment. To formalize the system, we started with the function model. As illustrated in the use case diagram, the user's interaction is grouped into 5 logical blocks. First, system access ensures the secure authentication via open banking APIs. Second, transactional management handles data ingestion. The core value lies in the analytics and forecasting block, utilizing machine learning for expense prediction. Finally, the visualization and AI assistant block allows users to interact with their finances using natural language, making the complex analytics highly accessible. Moving to the static structure, our class diagram is systematically organized around 3 primary layers. The domain layer contains immutable business entities. The service layer handles external interactions, specifically encryption and secure data retrieval from banks. The most critical is the ML AI layer. Here we implemented the facade architectural pattern through the ML Service Facade class. This provides a single point of entry for the business logic to access complex machine learning models, ensuring that the core system remains decoupled from the heavy AI algorithms. To ensure high manageability, the architecture is decomposed into logical packages. As shown here, the separation of concern strictly isolates domain entities for external integration interfaces and machine learning models. In the financial domain, this is crucial. It means data scientists can update or swap out predictive models in the models package without risking the stability of the bank authenticator or core financial tracking system. This modularity reduces cognitive load during system maintenance. The physical realization of this design is represented in our deployment diagram. We adopted a hybrid microservice approach. Our client requests pass through centralized fast API gateway, which handles routing and security. For data storage, we use a polyglot persistent strategy. PostgreSQL for strict ACID-compliant financial records, and the Mongo database for flexible, high-volume analytical logs. Crucially, the resource-intensive machine learning tasks run on a completely independent physical or virtual nodes. This ensures that heavy AI computations do not cause latency in the user's primary banking interface. Now, I want to focus on how this architecture solves the two main problems we identified initially. First, the black box problem. In finance, if an AI categorizes a transaction as an anomaly, the user and the regulator need to know why. Because we isolated the AI logic behind the ML service facade, we created a structural foundation to embed explainable AI tools, such as SHAP or LIME, directly into the pipeline. The facade intercepts the raw mathematical output, applies the explainer model, and delivers a human-readable justification to the user. Second, the issue of LLM hallucinations. To allow users to chat with their finances safely, our AI agent microservice implements the retrieval augmented generation or RAG framework. When a user asks a financial question, the system does not just send the prompt to LLM. First, it queries a vector database to retrieve the user's actual encrypted transaction history as context. The LLM is then forced to base its answers strictly on this retrieved data, practically eliminating the risk of fabricated financial advice. To validate our proposed architecture, we conducted a comparative functional analysis against two relevant industry baselines. Traditional monolithic applications offer high security, but they completely lack advanced analytical power and struggle to scale under load. Conversely, standard LLM integrated apps provide great conversational features, but they function as a dangerous black box and are highly prone to hallucinations. As you can see, our FinAI architecture successfully synthesizes the strength of both paradigms without inheriting their weaknesses. By utilizing a decoupled microservice backend, we achieved true scalability. Furthermore, by structurally enforcing the RAG pattern and encapsulating models behind the facade, we guarantee high algorithmic transparency and strictly neutralize hallucination risks. Furthermore, to provide a quantitative evaluation of our design, we conducted an empirical feasibility study with a focus group of 50 participants, including both potential end users and FinTech experts. The results were highly conclusive. Initially, users expressed significant skepticism towards autonomous AI advisors. However, when introduced to our explainable and AI interventions, user trust metrics improved by 64%. Moreover, 90% of participants felt secure knowing that RAG framework grounds all AI responses strictly into their personal data. Finally, from a technical perspective, 85% of the surveyed IT professionals confirmed that our decoupled microservice blueprint substantially reduces system latency risks during high-load operations, validating the practical viability of our approach. To conclude our research, we highlight 5 key takeaways. First, the proposed microservice architecture successfully integrates core domain logic, security, and complex AI models into a single unified ecosystem. Second, by decoupling heavy machine learning tasks from the main backend, the system achieves high fault tolerance and independent scalability. Third, implementing explainable AI through the facade pattern effectively resolves the algorithmic black box problem, ensuring strict regulatory compliance. Fourth, using the RAG framework minimizes the risks of LLM hallucinations by firmly grounding AI responses into actual user-specific data. Finally, this architecture serves as a highly practical blueprint for fintech engineers, specifically reducing their design risks and paving the way for our future work, developing a minimum viable product and conducting empirical high-load testing. Thank you very much for your time and attention.